Hey everyone, here is the second video of solving and graphing polynomial equations. This is the sequel to the number 1 video, so make sure that you have gone and watched that one before you watch this one so that we have a good basis of understanding before we get started on this one. So again, this is the number 2 video and it goes along with the number 2 worksheet, and let's go ahead and work through it. So we have 2x cubed minus 5x squared minus 4x plus 10 equals 0. And we want to solve this polynomial equation by factoring. So I see 4 terms here. That tells me that maybe grouping might be a good idea for factoring. So if I group this, my greatest common factor is x squared. And then I'm left with 2x minus 5. On my second group, my greatest common factor is a negative. Since there's a negative in the front, I need to take that out, but I can also take out a 2, and so there's negative 2, and then I'm left with, again, 2x minus 5. It's equal to 0. So between the two terms here, they both have a 2x minus 5, and when I take that out, I'm left with x squared minus 2. So I can set each of my factors equal to 0 and solve for x. So on this first one, I'll end up with, I'll add 5 to both sides and divide by 2. I'll end up with x equals 5 halves. Over here, when I add 2, I'll take the square root of both sides, but remember when you're solving and you're taking the square root, there is a plus or minus, so here we took the square root of 2. So our degree was 3, and we did end up with 1, 2, 3, since there are 2 solutions, 1 positive and 1 negative, 3 solutions. Let's look at another example. We have x to the 4th minus 3x squared minus 4 equals 0. I'm not going to do grouping here because I have an odd number of terms. But I can see that since my exponents decrease by 2 each time, this can factor into 2 binomials of x squared, so x squared times x squared. And we think, what multiplies to negative 4 but adds to negative 3? Well, if we get negative 4 and positive 1, so then we have an x squared minus 4, that's the difference of perfect squares. So you could choose to write them out x minus 2, x plus 2. Or if you wanted to, you could even just take x squared minus 4, set it equal to 0, and solve for the same way. Either way, it doesn't matter. So we have x squared plus 1. So if I set each of these things equal to 0 and then solve for x, I'll get 2 here. I'll get a negative 2 here. And then for this one, I'll get x squared equals negative 1. So x will equal plus or minus the square root of negative 1. But the square root of negative 1, do you remember what that is? It's I. So we'll have x equals plus or minus I, which is the square root of negative 1. So you'll see we had 4 solutions, 1, 2, and then there's 2 sitting right here, 3, 4. Notice that the solutions can be rational, as seen with the 5 halves, irrational, as seen with the square root of 2, real, and or complex or imaginary, as seen with this plus or minus I. Let's look at a couple of theorems. First, we have the irrational root theorem. And just to let you know, whenever we read through these, it'll probably seem a little bit confusing, but as we use them and practice them, it will make a lot more sense. Okay, so the irrational root theorem states if a polynomial p of x has rational coefficients, and a plus b times the square root of c is a root of the polynomial equation, p of x equals 0, where a and b are rational and the square root of c is irrational, then a minus b times the square root of c is also a root. So what you're looking for here is that if you have a root that has a square root in it, whether it tells you or not, there are actually two roots that are involved there, one positive and one negative. For example, that x equals plus or minus the square root of 2, it will always come in pairs. If there is a square root of 2 and one of them is positive, then there is another one that is negative. So square roots always come in pairs. Similarly, the complex conjugate root theorem states that if a plus bi is a root of the polynomial equation with real number coefficients, then a minus bi is also a root. So just like the square root will always come in pairs of positive and negative, I will also always come in pairs of plus and minus, or positive and negative. Okay, so let's write a polynomial function with roots or zeros of -3 and 4. If we have a solution of -3 and we have another solution of 4, we're going to work backwards from the way that we solved the examples at the top of this page. So before this step, we would have had this set equal to 0. So I'm going to add the 3 back over. And here I'm going to subtract the 4 over. Okay. Now I have two things that are equal to 0, and these are part of my factors. So if I multiply them, x plus 3 and x minus 4, that should still be equal to 0. And then if I FOIL them out, so I get x squared minus 4x plus 3x minus 12, which simplified, our polynomial with these two solutions of -3 and 4 would be f of x equals x squared minus x minus 12. So notice that when given two roots, the function that follows is x squared minus the two roots added together times x plus the two roots being multiplied, where, of course, here r1 and r2 are the roots. So if we had used this formula that was given to us, and r1 is -3 and r2 is 4, then we should be able to plug in x squared minus -3 plus 4 x plus -3 times 4. So here we would have x squared, and then -3 plus 4 is just 1, so we have a -1x, or a negative x, and then -3 times 4 is -12. So you see we get the same function. It works. Okay, so now let's look at another example. It's a little bit crowded right here, but this is another problem. Write a polynomial function with roots of 2i and 1. So remember that the complex conjugate root theorem tells us that if we have 2i as a root, then -2i is also a root. So therefore, this polynomial would be a cubic equation since it has 3 roots. So we have 1, and we have plus and minus, or positive and negative 2i. So there are 3 roots there, meaning that our degree for the polynomial will be 3. Okay, so we're looking for a cubic equation. So we can use this property up here that we looked at. Highlight it so it's easy to see. Okay. And we are going to write the polynomial function for this example with positive and negative 2i and 1. So first of all, we are going to work with the 2i and the -2i. So for those roots, let's just do one part at a time. So let's use the formula for just the plus and minus 2i. So we'd have x squared, and then it has minus. You add the two roots together, so 2i plus a -2i and that'll be times x, and then plus the roots multiplied, so 2i times negative 2i. Simplify this, we'll have x squared, 2i plus a negative 2i, that just equals 0, so that whole middle term goes away. But last we'll have plus a 2 times negative 2 is negative 4, and then I times I is I squared. So if I is the square root of negative 1, a square root squared cancels out. So this I squared is negative 1. So we have negative 4 times negative 1. So this is x squared plus 4. But we're not quite done yet. Don't forget we have the root of 1 as well. So we'll take this root for the plus and minus 2i and multiply it by the factor that gives us 1, which will be x, opposite sign, minus 1. We can FOIL that out. We'll get x squared, x cubed. I have certain students out there who like it whenever I make a mistake, so you caught me again. Okay, so we have x cubed, and then minus x squared, minus 4x, and then minus 1. And by minus 4x, I meant positive 4x. All right, so this is the polynomial that would give us roots of plus and minus 2i and 1. For this next example, we are going to do this one in class. It's a little bit of a lengthy problem, and I don't think I'll have enough space on here or time, so we'll do that one in class together. But I would like for you to try to do it on your own. Just to give you a hint at your final answer, we have 1 plus I, that means we should also have 1 minus I. If we have a square root of 2, we also have a negative square root of 2, and then we have a negative 3. So this tells us we have 1, 2, 3, 4, 5 solutions, so your polynomial should be quintic. So write out all your roots and multiply them together and tell me what you get whenever we see you in class. But we have a couple of other things we need to look at before you go. Okay, let's look at what happens when we try to solve x cubed plus 3x squared minus 10x minus 24 by factoring. I see 4 terms here, so my instinct would be to use grouping. So let's see what happens when we try to use grouping on this example. So between x cubed and 3x squared, my greatest common factor is x squared. And so when I take out the x squared, I'm left with x plus 3. For the second one, if I take out a negative 2, then I'm left with 5x plus 12. Okay, the parentheses are not the same, so this won't work, unfortunately. If you were thinking, well, you see that the 3 and the 24 also could be in common, and if you wanted to rewrite it and factor it, you also would not be able to use grouping. So rearranging and factoring by grouping here will not work. But that's okay. Let's look at what this paragraph says. Not all polynomial equations will factor using the factoring rules we have been using. So could we solve the example above by using the square root property, completing the square, or the quadratic formula? Well, unfortunately, no. So let's look at the theorem that might help us solve the polynomial equations that we cannot initially factor. The first theorem we're looking at is the rational root theorem. If the polynomial p of x has integer coefficients, then every rational root of the polynomial equation p of x equal to 0 can be written in the form p over q, where p is a factor of the constant term of p of x and q is the leading coefficient of p of x. So what this is saying here is if we don't know any roots, we can come up with possible roots. For example, x cubed plus 3x squared minus 10x minus 24. So what we're looking for are the values of p and q, and p is the factor of the constant term p of x, so the constant term. So for this first part here, the values for p will come from this last term here, this 24. And for the values for q, we'll know to look for that by looking at the coefficient of our leading term, so our leading coefficient, which here, that is just a 1, right? That's a 1x cubed. So for p and q, before we can divide values of p over q, identify what the p and the q are. So here p are going to be the factors of 24. So positive and negative 1, positive and negative 2, 3, 4, 6, 8, 12, and 24. All of those numbers are the possibilities for factors of 24. As far as q, for the factors of our leading coefficient of 1, the only factors of 1 are positive and negative 1. Yes, you will always have plus and minus in front of these. So let's look at the possible rational roots of p of q. So there we go. What we do here is we take each p value and divide it by each q value. Fortunately, there's only one q value here, and it's 1. So anything divided by 1 is just going to be the same thing. So here 1 over 1 is 1, and 2 over 1 is 2, and 3 over 1 is 3, and so on. So this one doesn't have a lot of extra. So the possible rational roots 1 through 20 values here, 1, 2, 3, 4, 6, 8, 12, 24. So this tells us that somewhere in here we've got rational roots for this polynomial. So let's look at an example. Let's find the possible rational roots of this function f of x. So the first thing we need to do is figure out the values for p. And p will be the factors of our constant, which is, here it's negative 4, but I'm just going to ignore the sign. So the factors of 4. So factors of 4 include plus or minus 1. We also can get 2 as a factor, not 3, but 4, and then that's it. So we have 1, 2, and 4. For q, here we're looking for the factors of our leading coefficient, which in this case is 8. So factors of 8, we could get 1, it's divisible by 2, it's divisible by 4, and then of course it's divisible by itself. So to find the values for p and q, p over q, I'll take each of the p values and divide them by each of the q values. So for the q of 1, anything divided by itself is 1, so we can start out with plus and minus 1, plus and minus 2, and plus and minus 4. Now if I divide each thing by 2, so 1 divided by 2 is plus or minus 1/2. 2 divided by 2 is just 1, and we've already got that one. And 4 divided by 2 is 2, and we've already got that one as well. Now let's divide everything by 4. So 1 divided by 4 is plus or minus 1/4. 2 divided by 4 reduces to 1/2, and we've already got that one. And 4 divided by 4 is just 1, and we've already got that one as well. So we need to now divide by 8. So 1 over 8, we don't have that one, so I'll add that to the list. 2 over 8 is 1/4, we've already got that, and 4 over 8 is 1/2, and we've already got that. So here we have 1, 2, 3, 4, 5, 6 possible rational roots. Okay. Notice that we are still using the word possible. That doesn't guarantee that any one of these is a rational root, but these are just some possibilities that would give us a place to start. For these last two examples, I'm not going to work through them in this video. I would like for you to also do these on your own, and then we will go over them in class. So we had negative x cubed plus 3x squared minus x plus 2, and then 2x to the 4th minus 2x cubed plus 31x squared minus 8x minus 6. All right, well, I will see you in class and answer any of your questions then. Have a great day. Bye.